Physics as we know it today is an attempt to interpret the diverse phenomenon as particular manifestation of general laws. Since its inception at the Renaissance, this has been an extraordinarily successful invention, to the point that after the impressive development in the first half of the 20th century, one could even conceive that all phenomena, from the atomic scale to the edge of the visible universe, could be accounted for by two fundamental laws only and two known laws. General relativity, which is a generalization of Newtonian gravity, and quantum electrodynamics, the quantum notion of Maxwell electrodynamic theory. But gravitational and electromagnetic interaction are long-range forces, meaning they act on objects no matter how far they're separated from each other. But the discovery of subatomic, nuclear, and subnuclear structure revealed the existence of other fundamental forces, which do not act or are negligible at larger distance scales. In the beginning of the 60s, there was no consistent theoretical interpretation of short-range fundamental forces as they are called. Bonaparte and I, and independently Peter Higgs, found a solution to this problem. Bonaparte passed away in 2011 and left me alone to tell our story.
That was confirmed by the magnificent experiment recently done at CERN. So, as I said, the long-range interaction that we knew were general relativity, electromagnetism, but there is a fundamental difference. Electromagnetism is valid in the region of quantum mechanics. And that was fundamentally a reason why we thought that we need to have a theory where long-range interaction and short-range interaction have a common origin. And that origin should be somehow analogous to electromagnetism. And electromagnetism is characterized by quantum particles which are zero-mass vector boson, called photon, as you know. And that means that these are quantum constituents of waves which propagates transversely to the direction of motion. And, the polarization is transverse, the electric field, magnetic field are transverse, and apparently this is a consequence of a local symmetry, and I will explain what that means. Therefore, we thought that from the long-range part, which should give rise to short-range part, we should go to Yang-Mills theory, which is a generalization of electromagnetism, which has the same content essentially, except there are many photons available, some neutral and some charged, and they can interact. Short-range interactions can be resolved quantum mechanics, for example, for this simple diagram in which I represent, this is a Feynman diagram, and this represents the scattering of two electrons. You read it from the time going from bottom to top, and this scattering is due to the exchange of a particle, call it Z, and it has a mass mz. Classically, this cannot exist because it violates energy conservation, but quantum mechanically, this is valid, provided there is a cutoff in time and in space, inversely proportional to the range of the mass. Therefore, this is a candidate of transferring short-range interactions in lowest order perturbation theory. Now, therefore, the question arises, if we want a common origin and if we want to start with the Yang-Mills field, that how are we going to get vector boson masses because there is this local symmetry which is supposed to prevent this to happen? Well, The simplest idea would be to use spontaneous symmetry breaking, which I will explain in a moment, which takes its origin in phase transition, but we shall see that it's more subtle than that. So let me first explain what is spontaneous symmetry breaking. Spontaneous symmetry breaking was well known in the theory of phase transition. For instance, it occurs in ferromagnetism. Ferromagnets are objects in which two neighboring atoms carry magnets which have a tendency to orient themselves parallel to each other. At high temperature, this effect doesn't give anything long range because of the thermal agitation. But when the temperature lowers, this tendency can orient the different objects globally and give a global magnetization. Of course, the system by itself has a dynamics which doesn't favor any orientation. It is isotropic. It has an isotropic symmetry, or it is, if you wish, rotational invariant. So this is a spontaneous symmetry breaking of rotational invariance in the low temperature phase. Of course, this has to be true for an infinite magnet and not submitted to any force. One can understand that a little bit more formally by writing a potential, which is a thermodynamic potential, in the plane Vmz, where it has a minimum at mz equal to 0. This is the direction of the magnetic field, of the magnetization, sorry. And this potential, the minimum of this potential, gives the indication of what is the value of the magnetization. Due to the rotational symmetry, you can go in the transverse region, and you see that at high temperature, as we said, the only minimum is at m equal to 0, there's no magnetization. However, when the temperature goes down, right, you see that in the VMZ plane, you develop a double minimum, which are actually in the transverse direction, joined by a valley indicated by the green arrow, and therefore, going in the valley doesn't cost any energy, while climbing the potential costs energy. Therefore, fluctuation of waves, let's say, which goes into the valley will have, in the long wavelength limit, no energy required to exist, while in the potential they will have to. So we see that in the language of particle physics, we would say there are two type of modes. We have massive modes when we climb the potential, and we have massless mode when the fluctuation run around the valley. This is a kind of, let's say, generalized Mexican head, if you want to have the picture. Now, the important point, however, is that there is an exception. Superconductivity doesn't have that property to have this massless mode, which is a point on which I'm going to insist a lot. This massless mode in superconductivity is eaten up by plasma oscillation, and I will not discuss this now, but you will see this is kind of a precursor of the BEH mechanism, which I will talk later. So this theory here is well known in phase transition. This type of diagram, as I said, occur very often generally in second order phase transition. And it has been, by Nambu, in a beautiful work, shown to exist also in field theory. I will not give the original Nambu description, but I will give the description of a simple model due to Goldstone. Goldstone took a potential which has the same shape, essentially, than the ferromagnetic potential. And you see one essential difference is that instead of having a symmetry in space, the symmetry is in two real fields, phi1, phi2, called scalar fields. I will explain a second why. And you see that what plays the role of a magnetization as spontaneous would be an orientation somewhere on the valley of the value of one of the fields, call it phi 1, that's the equivalent of mz. So this is the condensate, if you wish, that represents the analog of ferromagnetism. In the plane, it's a spontaneous breaking of a symmetry of rotation in the plane phi 1, phi 2, and it's called a scalar boson condensation because that orientation is in the space of field, and in space, ordinary space, there's no favored orientation, there's no orientation at all. That's the meaning of scalar. So we have something very similar here to what we have, and we can now again discuss what happens for fluctuation which climb the potential, and we'll see that this is just a massive mode, which now in particle calls the fluctuation little phi 1 around the expectation value mean the a massive mode whose quantum constituents are massive bosons, massive scalar bosons. And there are also massless bosons, as we encounter in the case of ferromagnetism, in which case these are called the quantum excitation of spin waves. Here, more generally, it's called Nambu-Goldstone boson. These are the massless fields which characterize, in quite general terms, spontaneous symmetry breaking. It's interesting to represent, and you will see why in a moment, this thing in a picturesque way. The first line represents the condensate, schematically, of course. The second line is the following. Suppose I orient half of these blue arrows a little bit with respect to the other arrows. That means in the direction of the valley. That costs energy because this is not a symmetry of the problem. But it can't cost a lot of energy because if I would rotate the whole thing, it would cost exactly 0 energy because it's spontaneous symmetry breaking, and that orientation is exactly the same energy by the fundamental symmetry of the problem. Therefore, this is this, and now I can go on. And the third line represents schematically a wave of short wavelength. So going back from short wavelength to long wavelength, we see that all that happens is that when we go back to long wavelengths, we hit a mode that has cost no energy. So this is our massless mode, and its constituents are the massless Nambu-Goldstone boson. Of course, you could do the same by climbing the potential, and I'm not going to repeat the story, and you would have, by stretching these arrows, this means that you climb the potential, essentially, that this case, you would need energy, of course, because you would increase the magnetization everywhere. That's a volume effect, and you would get massive scalar boson. Remember this type of picture because it will be useful in a moment, because now we are ready to talk about the BEH mechanism. And I will do that in a way first which is completely avoided, where I completely avoid mathematics. Not for too long, however, but a little bit. So let's take again the Goldstone boson. And the Goldstone, the Goldstone model, where I have redrawn the potential, and now I will impose the symmetry to be local. That means that instead of having a rotational symmetry in the phi 1, phi 2 planes, independent of the position at space, I can have I can now have a local symmetry. That means that any time, any place in space-time, I can do independent rotation of the system. you can say that this looks crazy. It is, except if you invent some field, which is called in general a gauge field, A, which essentially compensates the energy that you would need to do that by something that puts it equal to 0. That looks crazy in words, but is very simple, actually mathematically, but I don't want to go too much in mathematics. So, due to gauge field, we can impose a local symmetry in this problem if we introduce the required gauge fields. Then what happens to these two things? The mass is known, and this general characterization of broken symmetry, which was the Nambu-Goldstone boson. This is the second diagram. So this is our Nambu-Goldstone boson. Wrong, obviously. Wrong because now when I do this, I just apply a symmetry of the problem. Therefore, that cannot cost energy. Therefore, there are no Goldstone bosons. And there are no Goldstone bosons, meaning that actually this is just not a degeneracy of the vacuum. This is just a redundant description of the vacuum, which looks like spontaneous symmetry breaking, but that is due to the choice of the first row, which is a choice. And therefore, the Nambu-Goldstone boson cannot exist in a theory which has local symmetry, and it is fictitious Nambu-Goldstone boson. There have been formal proofs of that, including by Peter Higgs at that time. They were not referring to this type of thing, and actually this type of argument was made mathematically clear in my knowledge only much later, although there are indications, as you will see, already in '64. But this was, for me, the first paper I know where this is done properly is the paper by Elitzur, which is more than 10 years later. But this is a very simple way to understand why there is no Goldstone boson. And now, but what happens? If there's no Goldstone boson, something is wrong. Because if there's no Goldstone boson, there were degrees of freedom there. Where are they? If there are no Goldstone bosons, it's because of the gauge field. But if it's because of the gauge field, it is absorbed by the gauge field. It's the only way. How can it be absorbed by the gauge field? Well, we said the gauge field has the property of having zero mass as a consequence of local symmetry, and that also gives rise to the fact that there are only transverse waves. So the only way to be absorbed is to give a longitudinal waves. But if it gives a longitudinal waves, that's inconsistent with being massless. Therefore, the Nambu-Goldstone boson being absorbed, the degrees of freedom of the Nambu-Goldstone boson being absorbed in the thing, in the gauge field, give rise to a mass of the gauge field, and therefore give rise to short-range forces. And that is the program. That essentially is the VA mechanism when generalized to more general statement. Quantitatively, a few words. This can be done by Feynman diagrams, and this shows the propagator of the gauge field. And you see this gauge field associated to this local symmetry here interact with the condensate here, either directly, that's the first line there. So somehow the electricity is going down. Ah, no, it's there. Okay, so it interacts with the condensate either directly or with the intermediate thing, which is there in green, which is nothing else than the Goldstone boson. That's how it is absorbed, and that is the thing. When you write down, this is an expression which I just write down for these two diagrams which are there. The important point is that there are two pieces. The right-handed pieces is independent of the momentum, and that in field theory is simply the mass of the system. Therefore, we see that it has obtained a mass which quantitatively is easily computable. The first thing does many things, but I just want to retain one. This thing is exactly the same that what you find in quantum electrodynamics, and which is responsible for the consistency of the theory at the quantum level in a short, very short waving hand system. This can be generalized, as I say, to many Yang-Mills fields, because this is just a simple gauge field, and the mass is a little bit more complicated, but very easy to compute. It is also possible that a condensate would not be given just by a simple scalar. This would be a dynamical thing, and the same thing would happen. Nambu-Goldstone boson come and get absorbed and are becoming fictitious, giving again the PEH mechanism. The fate of the massive boson is nothing special because, of course, this has nothing to do with the symmetry. But we generally call it H in honor of Peter Higgs. But that is the same as the phi 1 that we had before. Of course, this is true in the classical limit, in the semi-classical limit. As you can see here, these Feynman diagrams can be read another way. This gives rise to a coupling of the H boson to the massive gauge vectors. Now, why do we do all of that? Why not simply put a mass to start with? Well, if you try to do that, then the theory is not valid quantum mechanically, because its departure, let's say in a very small way, is not consistent of the way it departs in quantum electrodynamics. Of course, things are much more complicated than that, because on that basis, we conjecture that it would be renormalizable, but that means consistent quantum mechanically, but it's much more complicated than that, because there's another problem, which I'm not going to time to discuss, which is unitarity, and it has to be done to all order, and that's the magnificent work done by Toft and Veldman, which shows that this theory is valid quantum mechanically, therefore that is a candidate for shortwave interaction, and it was used to do the electroweak theory and the standard model, which is there. I'm not going to describe it. There are, the first line is what contains the lepton on the left column and the quarks on the right column, and the first line gives rise to the ordinary constituent of the nucleon, and these are the other were guessed or discovered partially in the 70s. And then the theory of the electroweak is done by finding 4 massless gauge bosons in a given symmetry, and taking 4 scalar bosons. 3 of them are Nambu-Goldstone bosons, so they are absorbed, give rise to 3 massive gauge vector bosons, which are the W and the Z, which are responsible to the weak interaction. But the 4th one remains massless, and that is our photon. This is the electroweak. On the other hand, the quarks interact by themselves with strong interaction, which I will not describe here, and that gives rise again to a Yang-Mills theory with 8 gluons. As far as the electroweak theory, as we see, that leaves 1 boson, which can have a non-vanishing condensation value, like previously the phi, and has 1 massive scalar boson, the phi or H. So, of course, we have introduced a lot of fermions. These fermions, which are here, can get very easily a mass. That was already known by Nambu, but we can use the condensation phi to get a mass for the fermions. And this is essentially the electroweak model. and the standard model with all these particles and the electroweak and the strong interaction given by the 8 gluons. Now, all of this is nice, but it has to be discovered, and it was. So I remind you that the massive gauge boson coupled directly to the H boson, and that therefore we are going to get the Z and the W produced even at a semi-classical level. For the fermion, it's the same from the diagram which gives the mass. One can easily deduce the production of pairs of fermion, or more correctly fermion anti-fermion. And because the theory is valid quantum mechanically, one can also produce the gammas, the two photon diagrams through intermediate state, which are purely quantum mechanical. And now we'll flash essentially how this has been done by a few slides, which I'm not going to comment. There is no time for that, and it's not the object of my talk. It is at the LHC, where you have two circling beams going in opposite direction, which are schematically represented here, and which more materially are these big magnets, which runs on 27 kilometers. You have a lot of collisions between that. A lot means close to 1 billion per second collisions. Oh, that's remarkable. And these are analyzed in two detectors and was gone. This is a view of the Atlas detector. It doesn't explain how it works, but it shows you at least the size and the CMS. And all of this gives you the result that you want. The result is here represented here by a, actually you will see in a second, you will see that from 2011 to 2012, how the boson, the H boson appears, right? What you look is the decay of the scalar boson into 4 leptons, right? Due to two Z's. One of the Z is, as I say, not energy conservation or off shell, that's why it has a star. And you have, of course, many processes which gives that. That's called the background. This will be in blue. And so you look at every mass here, the background, assuming that the H boson does not exist. So you look for a mistake, right? You look where the boson, and here is the increasing of the mistake in course of time, which even if you're not a specialist, you can immediately see what it means. This red thing is the H boson at the relative mass. Other processes have been studied. The important point is that the result here is that everything seems to happen as if at the energy range considered, I don't want to say more generally, it behaves like an elementary particle. This is the thing which is important, because the discovery of the W and the Z, which was done in '83, would, in my opinion, be sufficient to say that the mechanism is correct. But it is not clear at that time whether we should choose about the two options that we presented in the beginning, either something which at the energy range considered can be considered elementary, or is it a more complex situation in which a condensate is not simply a boson, an elementary boson, and so everything seems to be that's about elementary. And that has a lot of consequences, which, of course, am I at 0 minutes to the end of my talk, I will not discuss. Thank you.